Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a theoretical physicist. So that means that I study the universe, the contents of the universe, how it all evolves, how it all interacts, everything happening inside the universe. It's a cool topic. I love studying cosmology and I love chatting to everyone about all of the cool things happening inside the universe. This is the point of Cup of Cosmology, wherever you're watching us from. We are here to chat all cool things happening inside the universe, and as always, any and all questions are extremely welcome. Hello to both Davids in the comments here. I do apologise for the slight delay. We were just running through everything and setting everything up. The two Davids, Paul, and great to see all of the regulars here. Thank you everyone for joining. Today's topic is going to be general relativity. It's a huge topic. There's no way I could cover general relativity by myself. So I have a guest with me today to help me talk about general relativity. Mark, you are now on screen. Welcome to Cup of Cosmology.
It's great to be here.
Great to have you here. Do you want to introduce yourself to the audience?
So my name's Mark Hindmarsh. That's my name. I'm also a theoretical physicist. It's no coincidence. And I was very working with us in Helsinki. The very early phases of in the first instance of the Big Bang connect to the fundamental structure of matter. Can tell about it from that may have been left behind by the
Okay, so we have a few, so thanks for the introduction. It's great to have you here. And as Mark was just saying, Mark works on early universe physics, which is really fun. We are getting some people saying that your audio is cutting in and out. We did notice we were having a few connection issues at the beginning of the stream. Now, hopefully that will sort itself out. There's not much we can do about that, I think. We have tried to sort out the internet. It should be stable, but there's always going to be some issues. So hopefully we can get a better connection as we go. I'm not sure if there's anything we can do really to sort out the choppy audio. Hopefully it will be stable enough. How's your internet looking, Mark? Any chances of the audio stabilizing?
Well, and my audio sounds fine to me. I'm not sure what.
Yeah, it's always a thing that streaming takes up a lot of bandwidth, so then it's cutting in and out. Okay, so let's just see what happens. If people say that it's bad and that we can't understand you, we'll try to figure something out. But for now, let's just see what we can do with what we have. So you mentioned that you work on early universe physics, which is really fun. Do you want to give us a few lines summary of what type of stuff you do with the early universe? Like, what exactly do you do? Because it's a broad topic.
Yeah, well, I'm working on from the very early universe, so most for the past few years, and that's especially been provoked, I guess, by the direct observation of gravitational LIGO. Just a few, more or less 100 years after their existence. So he was far ahead in many ways, and the great thing about they're sort of as well. I mean, they're very difficult. The fact that they're very difficult when they pass through it, but just on a tiny. But that also, this is the interaction. It means that they can, including the incredibly hot, dense plasma. So there are all kinds of interesting things that could have happened in the first nanosecond that in principle be observed. We could go and look for.
Yeah, it's really cool to think of all of the things we might learn if we ever measure these gravitational waves from the first few seconds of the universe. And we have had streams all about these early universe gravitational waves. We've had other people from the group joining us here. think you're the sixth person from the Institute now joining me on the stream. So we've covered gravitational waves. While it is a really, really interesting topic, it is not the main topic we are talking about today, although we will, of course, have to touch upon gravitational waves when we talk about general relativity. Okay, so we are still getting audio issues. Mark, maybe you can just try to refresh your browser. It will take you offline of the stream for a few seconds, but then maybe when you come back in, we'll have a more streamlined connection. So if you could just try to refresh your browser, we might be able to sort out the audio issues. Too many neutrinos, too many solar flares. Yeah, we're having just a few issues. There's always some interference, but we'll see if we can sort that out. Awesome.
Yeah, don't go away.
Yes, apologies everyone for the technical issues. There are always going to be some minor difficulties when we're doing this live. So just bear with us a few minutes while we try to resolve the technical issues here. Let's see if that's sorted out. We have you back now, Mark. Let's see how the stream quality is now.
Testing one.
Well, at least on my side, it does sound clearer. So let's see if that's cleared it up for everyone. But yeah, as people are saying, too many neutrinos, too many solar flares affecting the connection. Okay, so we mentioned that you work on early universe physics, that we're trying to figure out what we can learn about the early universe using gravitational waves. A lot of cool stuff. And very interestingly, and the launching point for our discussion today, you recently wrote a book. Do you want to tell us a bit about the book? Like, what was it about? What prompted you to write it? Tell us about your book.
Yeah. Well, it's a graduate textbook on general relativity. I wrote with my good Andrew Liddell, who's now University of Sussex, but he's now working still now, and I'm now in the summer. Yeah. So what prompted us? I mean, it was we taught this course. He taught what could be simpler than just writing and making a book out of it, and that's this year finished.
So the book is now out. When was the book published?
This year in May from
nice.
John Awkward Bookshop.
So how many years did it take to write this book? Like how much of an effort has it been to write this?
Well, it was a problem with being unable to devote to it. That's the problem. So that's why it took 10 years. Not was much less than that. Just in an academic career, things that interruptions and also life as well.
Yeah, always stuff getting in the way. So just recapping here, because I know we are still having a few sound issues. So Mark has written a book on general relativity, textbook aimed at graduate students, took 10 years to write because life gets in the way and physics gets in the way. And the book is now available at all your favorite bookstores. Please go and buy it local, don't buy it from Amazon, or buy it from the publisher directly. So we do now have another general relativity textbook out there. So there are a lot of different general relativity textbooks on the market. So what sets yours apart, other than you wrote it? Like, what is the key argument behind yours? What sets it apart from the others?
Well, I think one of the things we note when teaching it, people really struggle with that you need tensor calculus and differential, and so we were to sort of students to that gently, make the missions as transparent as possible. So and because we taken by students who would not to study astrophysics, they just wanted to study generally interesting interesting and cool. So behind it, that would be for people who wanted to specialize in cosmology. That's special about it is find out lots of things scientists, and of course I'm in Finland, contributed to general relativity into the stand, in particular the Finnish physicist Gunnar Nordstrom.
So want to jump on that, but before we do that, someone's just asked for the link to your book. Do you have it at hand? Because I actually do not have the link at hand, and I should have prepared the link. People in the comments do want the link to your book. I forgot to prepare the link, so if you have it at hand, we can drop that in the comments. Send people to the publisher to go buy the book. Yeah, let's see if we can drop a link here for people. And then we can go back to some of the interesting things you mentioned there. So I do think it's really nice to have a self-contained textbook without all of the mathematics you need to understand general relativity, because general relativity is a big topic. As you were saying, there's a lot of math involved, and it's very easy, especially as a graduate student, to get lost in the mathematics that you need to understand it. So having a book that tries to provide an introduction beyond just all of the crazy math is very, very, very useful. So as we're looking for the link, there are a couple of people asking the same general question. Okay, thank you for the link. I will just copy that into the chats. There are a couple of people asking the same general question. Before we get into the comment you just made about Nordstrom, what is the difference between special and general relativity? Like, people often mix up the two. Is general more important? Is special relativity more important? Can we get a few words about the difference between these two?
Yeah. It's a very good question. It's not a quick answer, just based on which wouldn't make the kind of trouble one considers in the two theories. The difference is that is a theory of gravity, and the specialness of general relativity, the others called general, with the way that I started thinking about how can you have the results of physical if you are moving a system that you're trying to measure with another observer. I'm thinking about this because as a teenager, he wondered what it would be like. Could you catch up with a light wave so that the electromagnetic wave was just in your living room, and he just that would not be. So that got him to thinking more generally. What it to make an observation, particular to between observers who are moving. Now, the theory, the movement to constant and any movement, so in any kind of acceleration. So it's the difference between them. And the amazing thing is, if you just start from that idea, then general relativity to be a theory of gravity, and you didn't ask this question.
Yeah, so they both do have this relativity in the name, but as Mark was just saying, special relativity really is about moving at constant speed, and in general relativity we add in acceleration, and then it becomes gravity, because there are connections between acceleration and gravity. And usually when you're learning about those things, you start with special relativity to get a grasp of the concepts, and then you move on to general relativity, which is also the kind of progression that Einstein did in the theories as well. So we move from one to the other. They are similar, they have some shared concepts, but we do need to separate the two. So I want to go back to what you said when you mentioned about your book. You said writing the book gave you an opportunity to learn about stuff you hadn't really thought about, including Nordstrom, the Finnish physicist. So Nordstrom is someone who many people perhaps have never heard of. So do you want to tell us a bit about who this is, why he's important, why he appears in your books? Just so people get an idea of who we're talking about here, I'm going to flash an image of him as well. So once it loads. This here is Nordstrom, and he was a Finnish physicist. This is the Wikipedia page photo of Nordstrom. So Mark, do you want to tell us who this is, what you learned about him, why he's important, like why should we care about Nordstrom?
He was indeed a Swedish-speaking Finn. That's what Swedish, and the Finns with Swedish name Swedish, but actually, and I name in a solution equation for general. It's a black hole with electric charge, and that's, so he discovered that after published, and it's because he on gravity more or less contemporary. So it's in PhD studies, partly in the Leiden in the Netherlands. Hot place to be, the 1900s. So that is studying after waiting from Aalto was there in the Institute of something of Helsinki. So, person who come up with theory of gravitation. So it was a theory of gravitation satisfied this that all observers' state of motion should compare the results of their observation. So it's relativistic in that sense, accelerating observers precise for physical observation. So it was the first couple of years before so 1913, and it wasn't he didn't was in contact with the top physicists of his, including Einstein, and I very high regard, and of course held Einstein very high, him for the Nobel Prize for the prize, but not for relativity. So done, I think.
Yeah, so I think it's really interesting to think here. So Nordstrom did propose his theory of gravitation 1 year before Einstein proposed general relativity. And for some things, the model was very accurate, but not as accurate as general relativity. This was especially seen when we had the solar eclipse in 1919, where we could see the bending of light rays around. So once you have a solar eclipse, you can really see how the light rays are coming from the sun. And here we could see the bending of light due to the gravitational force, which is exactly what general relativity predicted, but could not be explained in Nordstrom's gravitational theory. So at that point, general relativity became obviously the more dominant of the two. But it is really interesting here to consider that, you know, he had his own model. And as Mark was just saying, the two did not see each other as competing. In fact, Nordstrom and Einstein got on very well among themselves. And Nordstrom nominated Einstein for the Nobel Prize at least twice. So even though they had competing theories, they actually weren't seen as competitors and rivals. They worked well together. So that was nice to see. And I've heard that one of the reasons that Nordstrom's contributions are often overlooked is because he mainly published in Swedish, as Mark said just now. So then that meant that his work didn't get as much international recognition because it wasn't in the right language. So I see someone here proposing that maybe I could cut your video to get better audio. Unfortunately, on the free version of Restream, which is the version I'm using, I can't have audio-only connections. If I shut off the video, we lose Mark's connection entirely. So unfortunately, that's not something that we can do because I'm on the paid version of Restream for now. So we've covered a bit about Nordstrom, about your book. So maybe we can ask the really basic question here. What is general relativity? If you had to summarize it in a few lines, which is difficult because it's a big theory, what is general relativity in a nutshell?
So I've just tried switching from one device to another to matters. What is general relativity? It is, as I was saying, gravity. That's really what it is. About observers comparing moving is kind of a statement of the framework of the theory, but it's physical content. It's a theory of gravity. The theory of gravity, which being describing the time themselves. So the new theory is that there are bodies exert, but the Einsteinian picture of gravity, and this was not really in the Nordstrom theory. Space and time are curved, and it's in straight lines through a curved space. That's why things appear to doesn't look like a straight space. A straight line of general relativity in space. So it's a theory by curving, and it tells you how is it that curves space, that it's matter, and various properties of matter, which intensity of matter. But actually, in fact, there are 10 different properties to calculate the exact universe. Is the famous
Yeah, so I just flashed the equation there, but just to recap what you were saying there, general relativity is a theory of gravity, and it very elegantly maps the curvature of space-time into what we call the gravitational effects. And there's always a sentence that is like, summarize general relativity in one sentence. And the sentence that I was taught in this case is, space-time tells matter how to move, and matter tells space-time how to curve. And that's basically general relativity in a sentence. And we talk about it a lot in words here, but this can actually be expressed in equations. Of course, there are Einstein's general relativity equations, and it's the one that is actually in my banner image. So this is what you can see on screen now. This is my banner image from YouTube, from Twitter. designed by Sonia Hiba, the amazing Sonia Hiba. This is my banner image, a lot of Easter eggs. And you can see the equation here, G with some indices mu nu equals 8 pi T mu nu. And I put the actual real one here where you'll see there's a G and a C difference. And these are things that we normally just set to 0. Sorry, so we set to 1. G, speed of light is 1, G is 1, we get rid of them. And what this basically tells us, the G part on the left-hand side is the curvature of the universe, and the T on the right-hand side gives us the matter and energy content of the universe. So it relates the curvature to the matter content. And as Mark just said, this is actually 10 equations, not just one. We can really pull out 10 equations here, but this is kind of the condensed form of writing all of these equations. Cup of Cosmology logo is hidden there. Yeah, there's also a cat that people need to identify. There's a bunch of Easter eggs hidden in the logo. Sorry, in the banner and in the logo. Question from Paul here. If gravity bends, just lost the question, it moved out again. Okay, question from Paul here. If gravity bends space and acceleration is equivalent to gravity, does my accelerating curve of space, or at least perception of it? So let me just rephrase that there. So basically, what is the connection here between the acceleration, the curvature, and the gravitational force? Can you explain the connection between these three topics?
Acceleration is important. It is a sort of about, again, the gravitational force. So thinking was always very, and so he thought of sealed in a space rocket, and how we between the lift and the being stopped at the ground. So of course, if you could, for example, your weight would go up if you're upwards and downwards. So, a sealed space rocket, know what your weight is, don't know where you are in the. Einstein came to the conclusion that actually, at least local, at least in a small region between the gravitational force, acceleration and gravitation are just convenient labels. You can call it acceleration force. It's providing. So I'm not sure that precisely gives an idea of how acceleration are connected. I hope.
Yeah, I think it's also something we can all think about. If you've been on a roller coaster or on a plane that suddenly goes down, you feel yourself lifting up in your seat, right? If you're on a roller coaster and you hit that big drop, you feel yourself lifting up, and it's almost like you're achieving some type of weightlessness. And this is exactly what is happening. The acceleration of the roller coaster is counterbalancing somewhat the gravitational force. As Mark was saying, you can also feel this in an elevator if you're going up or down. So then if you define something as acceleration, or if you define it as gravitation, it's essentially the same thing within the framework of general relativity, right? It's just sometimes you talk about acceleration, sometimes you talk about gravity. They are essentially the same thing. And what general relativity tells us is that acceleration in the universe is generally caused, or the one that we identify as gravity, is caused by curvature. So curvature, objects with mass bend space-time. This curvature tells objects how to move. And once objects are moving here, you have this gravitational force or acceleration due to the curvature of space-time. So that's just wrapping up what Mark said. I'm just repeating it here because of the slight connection issues. I'm just repeating it to make sure that between both of us, they might hear half of the words. So then maybe that can answer it. We have a nice question here from James that you already mentioned a bit before. So Einstein's general relativity makes several predictions. One of them is gravitational waves. Someone's asking, how did Einstein predict gravitational waves? Are they part of general relativity? Was Einstein alive for the detection of gravitational waves?
So yeah, Einstein, after publishing the theory in sort of late 90s, pretty quickly realized that there were these waves, electromagnetic waves and so on. And he was able to find that. So gravitational waves from 1 year after the public. But the strange, he was never quite convinced between whether it was a funny about the equation and anything physical or something physical there. And in fact, it wasn't really until the people became convinced that actually they could, the wave motion is supposed to transport from one place to another. Only in the 1950s that people really actually, yes, there was energy in that gravitating in motion. And in addition of that, because mirrors are by black holes merging light years away. Only but fractions of a meter. I mean, it's a visual proton, but nonetheless, we that small motion.
Yeah, so it's fun to think that when Einstein predicted gravitational waves, he saw that they are a mathematical thing you find in general relativity. But Einstein himself wasn't sure if this is something physical or just a numerical quirk that happens in the equations. And by now, 100 years later, we have actually measured gravitational waves. We know they're a thing. We did have indirect proof of gravitational waves beforehand, but now we finally have direct proof of gravitational waves as well. So this was one of the predictions of Einstein's general theory of relativity. On that question, what other predictions does general relativity make that we have been able to test? So what else, like why do we believe in general relativity? What has it predicted? What have we checked?
Yeah, question, because indeed, why does everybody believe in it? I think you already really nice and shows how science, so general relativity brings as it but actually, as you said, so that's a you can go and test, and then you can decide which theory is wrong, or wrong, and which theory is not the best way of about it. Bending and precisely predictable, and always that there's a so if you look at from the sun, the light signals to get to us might have thought, and that's just from the geometric distance, partly to do with traveling on a curved trajectory, which is purely general to do with the time, the time of the equation. So let's see, sort of test that you would do to exam, and I think I'm probably going to I'm not, haven't come to the third. Oh, yeah, the third is about all. So in the orbits of planets, a single planet around a single star, it's our precise ellipse, but Mercury not to be. It doesn't join up on itself. Furthest from the sun, it doesn't matter which one you take. Point nearest the sun is the orbit is called the perihelion. Changes a small measurable amount. Mercury orbits, and it's Einstein calculations. Einstein did was to calculate that precession, as it's called, and he got must have been incredibly. So I think those are the basic tests, but there's which we can go into if you like.
Yeah, so it's really cool to think. So when Einstein initially made his theory of relativity, there were three main predictions, just recapping the three predictions here. And then later others were added. And these three are considered the three classical tests of general relativity. There is the deflection of light. So because light moves on a curved surface, it gets deflected. This is something that we can best observe during an eclipse when most of the direct light from the sun is blocked. And what you just see is the corona. And from this, you can actually measure the deflection, which was first done in 1919. And this is the image I keep flashing here. This was the first eclipse that was used to measure general relativity, the 1919 eclipse. So that is one prediction that we have measured from Einstein's general relativity. As Mark was saying, another one is related to the orbit of Mercury. So as Mercury orbits the sun, it doesn't always come back at exactly the same point where it started. There's a slight precession. It basically means the orbit is moving slightly. The way it's moving can be explained by a lot of different contributions, like the whole motion of the solar system, the planets within the solar system. But even if you add all of those up, you're still missing a tiny part, which can be explained if you add general relativity. And the other classical prediction was the way light gets redshifted. So light is a wave. This wave gets distorted as it travels through curved space-time, and this leads to the gravitational redshifting of light. There's also the prediction of gravitational waves, which we have now measured. So general relativity makes a lot of predictions, and we have measured most of them. In fact, it is one of the most well-tested theories we have in physics. Every test we've tried to do, so far we found that general relativity works. So there are some questions and people asking for clarifications here about how we relate acceleration to gravity. It seems we've confused some people with this concept. So we had a question by Paul just now that the gravitational force falls off as the distance squared. So the further away you are from an object, the less you feel the gravitational force. How does that fit in with acceleration? Because acceleration doesn't seem to drop off. And now we have another question here of what's the connection between gravitational waves and acceleration? So I think we've confused a few people with the concepts here of gravitation and acceleration. So do you want to address those two questions there, Mark? So basically, how does acceleration fall off in the same way gravity does? And how is this connected to gravitational waves?
So it's not gravity that cause you to accelerate. For example, in the universe, so electric forces, which also correlations. So, in the acceleration, give the impression that acceleration was highly due to gravity, and throw things out the back of its exhaust. So ultimately, that's actually you think about it, about the interaction of atoms in the rocket exhaust, with it. So they're all bouncing off. And if you think about the bouncing off each other, that's back to the electromagnetic force. So the electromagnetic can cause you to these particles so true that if a gravitational wave is by your detector, thing LIGO are basically big masses, big pendulums, so very very fine. So when a gravitational wave can one frame of reference about can exerts causes to it to accelerate. Of course, that's only one thing at it. From the point of view of sitting on the surface of the Earth, or looking at the
Yeah, just lost the last word there, but that's fine. So yeah, I think here when we talk about acceleration and gravity being the same thing, as Mark was just saying, what we need to be aware of is that what we're calling, it's basically the curvature of space-time, the effects of the curvature we interpret as acceleration. So the gravitational force is kind of this curvature of space-time, but you can't directly say gravity equals acceleration, but the effects are the same. So that's how we do the connection there. So as Mark was just saying, a gravitational wave is going to be a ripple in space-time. When this hits an object, it is going to cause an acceleration. It is going to cause a movement. So the wave itself is not in any way the acceleration, but it's the moving curvature of space-time. And then when that curvature of space-time hits you, that's what causes the effects that would be similar to acceleration. In the same way, if you have a massive object that is curving space-time, the closer you are to it, the more gravitational force you're going to feel. As Paul was saying in the comments, gravitational force falls off the further away you are from an object. If we draw the parallel here with curvature, which is what Einstein taught us to do with general relativity, the closer you are to this massive object, the more curved space-time is, and the more acceleration you'll feel. The further away you are, the less curved it is, and the less acceleration you'll feel. Hope that answers the two questions there, but it is, don't worry to anyone here who's confused by it. This is a very, very complicated topic. You know, general relativity, there's a reason it's a 1 year long course in a lot of universities. It is, we're trying to break it down to 1 hour here. There's a lot to be said about general relativity. As James is just saying here in the comments, we would need 10 shows on general relativity at least in order to cover all of the fun things. So we're really just trying to give an overview here, a broad picture. But it is very, very complicated when you get down to it. So don't worry to anyone who is confused by this. We did have the very nice comment here. We were talking about the precession of Mercury. We've been asked why Mercury of all the planets, given that, you know, all of the other planets could also be good experiences. So why do we use Mercury?
Very good question. That's a really good physics question. The answer is that general relativity, other effects, the ratio of the planet to the speed of light. So the effect is bigger the faster it moves. Is the fastest moving planet, biggest for Mercury. So it was measurable in the true. Actually, not sure. Next fastness. I'll have to go there.
The next fastest, so by Kepler's law, the closer they are to the sun, the faster they move, right? So the next fastest should be Venus.
It should, yes. Yes,
But
I don't know whether it's.
Yeah, there's always some competing effects here. So in general, the closer you are to the sun, the faster you move around it. But then there are some competing effects because you have the gravitational force of other objects distorting things. But as a first approximation, we can say Mercury is closest, it's the fastest. Next up would be Venus, assuming I remember my planet ordering properly. It's always like the seven dwarfs, right? You trail off halfway through. Okay, so we've done the thing of general like gravity, acceleration. So I also want to come back to something that there was a question or comment made tongue-in-cheek by one of our regulars who always makes jokes here. And it's a comment we hear sometimes that, general relativity is just a theory. I just want to mention that this is, again, how different people use the word theory. In science, we mean something specific with theory, which is not the same as a hypothesis. But do you think there's anything left to test with general relativity? Is there anything that would prove general relativity wrong? Like, what's the future of general relativity in your opinion?
That's a very good question. So it's a question. I think it's a question of. So we know that works, system, scale, and we on up to more or less the size of the observable universe for everything we see. But there is, but on very large distance, universe, which instances know about the expansion of the is not slow the speed of the very distant galaxy rather than slow. Expect from if the Big Bang explosion, then the gravitational pull of all the things rushing slow them down, and the growing apart from each other should. But that's not happening, which means that at some way gravity distance is so that actually accommodated in general relativity, addition of logical constant, but you find just very unsatisfactory. So in general relativity of the universe is that I think is of cosmologists' minds. A satellite going up pretty soon, I think in 2024, called Euclid. It is to general the predictions of general on the very largest scale. That I guess cosmological constant perhaps be a bit boring. But yeah, I would still find that extremely interesting.
Yeah, it's definitely interesting here to think about this. So as Mark was saying, general relativity has been well tested on local scales, everything we can observe. But there is the fact that the universe is undergoing accelerated expansion. Now, if we just consider the gravitational force, things should collapse inwards. This is not happening. So there is something that is causing things to move away. There are different ideas here. The most prevalent one is dark energy, which makes up for 70% of the energy density of the universe and would be driving this accelerated expansion. This comes in the form of adding a cosmological constant into Einstein's general relativity. However, you can also accomplish the same effects on large scales by modifying general relativity. This is what we call modified gravity. And as Mark was saying, on these really, really big scales, this is where we can still test general relativity. And there was this satellite set to launch. It was actually supposed to launch in 2023, but it no longer has a rocket to go up on. So they're still trying to find a new rocket for Euclid. Euclid is a mission that is going to measure the distribution of galaxies today and throughout the cosmic history. This will give us a really big understanding of how dark energy behaves, or the cosmological constants, and it could actually falsify our idea of dark energy. In which case, we're back to the idea of not understanding the accelerated expansion of the universe, which again brings us back to general relativity. So I've often talked about Euclid as a test of dark energy, but it is also a test of general relativity, because it tests really the whole expansion of the universe. So my question was a very broad question there of like, what is the future of general relativity? Now, general relativity is a well-tested theory. It's held up to every test we've thrown at it so far, but there are still places where it needs to be tested. Another one that I find very interesting is what we call the extreme regions of the cosmos. So we know that we have this cosmic web structure. There's regions of the universe that have more matter. This is where all the galaxies lie. And then there's voids in between this cosmic web. And there are a lot of people working to see if general relativity works as well in the voids and in the superdense clusters as it does on average where we've observed it. So those are also places where people are looking to modify general relativity. Now, the thing is, because of all of the successes of general relativity, anything you do beyond that still needs to replicate these successes and then some, right? If you come up with a new idea that can't explain the precession of Mercury, then we have a problem. So it's very hard to find something that works as well as general relativity and can do something for us that general relativity can't. But as always in science, any theory can be falsified. If we find evidence that no longer supports general relativity, then we have to change our theories, because the theories always have to be complicit with the data. If the data does not support a theory, then either you've messed up your experiment or you've messed up your theory. So even though it is our best theory for now, it doesn't mean it's absolute. But it has lasted 100 years, and it's survived every test we've thrown at it so far. So we've talked a lot about what general relativity is, how we can explain it as curvature. What else do you think are the most important things people should take away about general relativity? Is there something else you think, oh, people should know this about general relativity?
That's a good question. Well, I think that it's sort of say that it can't be the end of the story. It isn't that kind of what many people mental problem to work on. Very difficult to make general relativity consistent with the postulates of quantum mechanics. And that, of course, topic of another. It's not a quantum theory, and that's for a theoretical physicist, because every other about is a quantum theory. And so, last Nobel Prize for physics for quantum theory. So I'm just on how important it is. So that if you want a problem to work on, that's one of them. But I think it was too hard.
Yeah, that's definitely like something that I would love to have, but it's definitely something that we're not going to do yet. So this is the problem, right? We like things to work in the quantum world, which is the world of the very tiny stuff. And gravity helps us understand how things move on big scales. And when you try to put these two together, it doesn't work. We don't know how to put them together. To do this, we would need quantum gravity. We're still trying to figure that out. We haven't got there yet. If anyone's figured out quantum gravity here in the comments, do let us know, because best physicists haven't been able to yet. It's really difficult to figure out what to do with gravity on the quantum scale. Now, with gravitational waves, we get a bit closer, because we now have the thing that, with all other forces, we know there's a particle that carries them. So then we can ask the question of, is there a particle that carries a gravitational force? And if so, is that what gravitational waves are made up of? Are gravitational waves made up of these tiny, tiny particles known as gravitons? We don't know. We're still trying to figure out how to put the large world and the small world together. And this is something that I think all of us would be very, very, very happy to see. But we're still working on that. So that is definitely an open question there. So we have a question here about black holes, which is a bit off topic, but not completely off topic, because we are talking about gravity and what is a black hole if not just gravity. So what someone's asking, Paul is asking here, when you cross the event horizon of a black hole and you look down, what would you see? This is a fun question. So what would you see if you cross the event horizon of a black hole?
Yeah, good question. And I know the answer to this. But what I think is the case, that light doesn't get out. Outgoing, not possible for a photon move outward inside a black hole. So I think the answer, and if it was a sufficiently large black hole, so the parts on the way in, it should be some time for you to black hole. And I think they're coming from the center of the hole. So I don't think dark.
Yeah, the fun thing here is we can't really give a real answer because we don't know what happens inside a black hole, because the event horizon is the point at which our equations break down. Once we're inside a black hole, we have no idea what happens. We can guess based on how we think stuff behaves, but inside a black hole, we don't know what happens. But yeah, if there's a big gravitational force and everything is pulling downwards, then light can't come back to your eye. So would you even see anything? Would you see the light falling around you? It's a fun thing to ask. And you pick up any sci-fi film and they'll depict it differently. So it's still trying to figure out what happens inside black holes. Problem is, if anyone ever jumps into a black hole, you won't be able to send us back the information. So do not do that in the name of science, because you won't be able to tell us much. You probably don't want to jump into a black hole. Okay, so we're almost at the 1 hour mark here. Just before we wrap up, Mark, is there anything else you want us to know, either about general relativity or about your research in general? Is there anything else you want to put out there into the audience?
I think we've had a great hour. You've been a good host in
thank you.
Interpreting for the masses, the audience out there. So it's been great fun. Thank you very much for.
Yeah, it's been really great to have you here. Great questions from the audience. And, we can leave with one takeaway here. We think we've understood gravity. People are used to this, you drop a pen, it falls down. We've all seen Roadrunner where Coyote falls down, but only if he looks downwards, otherwise gravity doesn't exist. So we have this idea that we kind of understand gravity, right? But gravity is the hardest force to understand. We haven't figured out how to make it a quantum theory, but we do have the theory of general relativity, which gives us a really good understanding of how we can explain gravity as a function of the curvature of the universe. It's really elegant. It relates the curvature of space-time with the mass, with the gravitational force. It's a really elegant theory. We would need 10, 20 streams to do it justice. And in this 1 hour, hopefully we've given you some sprinkling of an idea of what general relativity tells us. But there's a lot to unpack. So if you want to know more about general relativity, go buy Mark's book. This is what prompted this stream. It is aimed at undergraduates, so some previous knowledge is required. But in general, it's always good to have more textbooks on general relativity. So there's a link somewhere here in the comments. I'll post it below once the video is live as well. So do go out and buy Mark's book if you need another general relativity textbook in your life. And that does bring us to the end of the hour. So I just want to announce that next week, I have another guest on Cup of Cosmology. Next week, we're going to be talking about a really, really strange concept known as cosmological bootstrapping. It's a really difficult concept to understand. I have no idea how we're going to explain it in the stream, but I am here for it. So next week, same time as always, that's 8 p.m. Finnish time, 7 p.m. rest of Europe. 1 p.m. if you're on the East Coast, 10 a.m. if you're on the West Coast. We'll be live talking about cosmological bootstrapping. I'm definitely going to need some help with that one. So big thanks to you, Mark, for joining. It's been great to have you on the show. And if you want to come back another day and talk about anything else that you work on or more about general relativity, you are always welcome back on the show. So with that, let me say thank you to everyone here for joining, and apologies again for the technical issues. I actually think it is on Restream's end because the whole interface is buggy today. So I don't think it's actually on our end. But in any case, thank you everyone for bearing with us throughout the slight technical issues. And I hope to see you all again next week. And I hope in the meantime, everyone stay safe and take care of each other.